the total current as zero. Typically, like we identify whether there is a reactive current and dissipative current, and we put only the dissipative current as zero. So
sorry, what is an adaptive current?
Reactive current.
Oh, reactive current. Okay.
So here we put the whole current as for equilibrium state. So do we check it by the like Fokker-Planck equation here, or do we know that there are only reactive currents and reactive currents?
So you can check. I mean, by definition, an equilibrium stationary state is one in which there is no net current whatsoever. Okay. Now, because an equilibrium stationary state respects time reversal symmetry, so therefore you cannot have current of any sort. Net current, I mean, the average current should be zero. You may have fluctuations, but that's fine.
So we just identify the current and we put it equal to zero.
Yeah, I would say that is the way to go about it. I mean, there is no, you see, the stationary state is determined by assuming that there is no current. And then with that, you know, I mean, by definition, an equilibrium stationary state doesn't have current because I think there are many ways to show it. One way is to say that, okay, it satisfies detail balance. And if it satisfies detail balance, then there is time reversal. So, okay, maybe this is something that I was not planning to do. But, okay, maybe I can just quickly mention. So, equilibrium would mean that it requires a little bit of language. So, I don't know how many of you are familiar with this language of Markov processes which are defined by these transition rates, the probability per unit time to go from one configuration to another. So, a Markov process is completely characterized by these rates and the one-point distribution. So, if you are in equilibrium, then it satisfies this particular condition, which is known as the condition of detail balance. How many of you are familiar with this language of stochastic process? Okay. So this is what it means to have equilibrium. So this is known as the detail balance condition for a Markovian process. So that is to say that you take a, you know, if you look at a sequence of configurations and so on. So if it is Markovian, so then what is the probability that you are here? It depends on just a situation one step back. It doesn't depend on how you got to. So suppose you want what is the probability that you are at C double prime? It just depends on C prime. It doesn't depend on how you got to C prime in the first place. So these processes are characterized by these two quantities. This is the probability of finding configuration C in equilibrium. It could be stationary state also, and this is the probability per unit time to go from C to C prime. And if it satisfies detail balance, I mean this is the condition of detail balance, and then you can show that if you take a closed sequence of closed loop of configurations, let's say, or okay, you don't have to even take a closed loop. Like, let's say you take this one, okay, this one. And you ask what is the probability, what is the net probability current in this direction? This would be J forward, let's say. So this would be P equilibrium C W. Okay, just to save my time, let me reduce one configuration. Doesn't make two configurations. Okay, so this is the probability current, you know, the current in this direction. So, and the backward current will be and when the detail balance condition is satisfied, these two things are exactly equal to one another. That is to say that you cannot have a net probability current. Okay? whatever goes this way, it comes that way. You can take it around a closed loop. It will be the same. Maybe it's best that you take a closed loop. That will be, I think, easier. So then C double prime, there will be C to C prime, yeah, and this one will be C double prime to C prime to C. Sorry, C to C double prime. You can check that these two, so there is no net probability current around any closed loop in the configuration space. Okay, so maybe we come to this noisy Kuramoto model that we were doing. So did some of you check whether the solution that I wrote down for the stationary state, whether it makes sense and so on? I mean, of course it makes sense, otherwise I would not have written down. But, okay, so let's just recap a little bit, because perhaps. So what we were doing was, what we had done was, initially we were considering this model, this the barebone Kuramoto model. And these were fringe disordered random variables taken from a distribution G omega that had this property that it is symmetric about the mean. Okay. And we were asking for the following thing, that does this system show synchrony in the steady state? And by synchrony, what we meant was, we were looking at this order parameter RT to the I psi t, and we were asking whether as t goes to infinity, that is at large times, this guy, it takes up a value between 1 and 0. That is to say that does the system in the stationary state, so does that system show global synchrony? And what we found out for this model is that indeed it does show global synchronization, in the sense that if I plot this time dependent R as a function of k, then there is a critical coupling above which the system shows synchrony. And we found out an exact formula for this guy, critical coupling, which was 2 by pi g0. And we said that when the system is, when k is smaller than kc, it doesn't synchronize, and when k is larger than kc, it does synchronize. Okay, so that was the bare Kuramoto model, and then we looked at the case where you introduce a noise in the system, and so this was a quench disorder, source of quench disorder, and this is anneal disorder, and this noise, it satisfies these conditions. And we were interested to know how does this value of Kc shift in presence of this noise. So the picture that we had drawn, this is what we anticipate to happen, is this is my K and this is my Kc, which is 2 by pi G0. And the question is, what happens when you introduce noise in the system? And we argued that this point has to shift to the right. So the question is, what is the form of this curve, Kc as a function of t? How does this curve look like? What is the functional dependence on d? This is what we were after. And we wanted to solve this equation by looking first at the equation of a single oscillator, single non-uniform oscillator, omega minus a sine theta plus eta, for which we found out that the stationary distribution has the form the same quantity. This is a constant to be fixed by invoking the normalization condition. And we see that when the frequency is equal to 0, then you have the equilibrium stationary state e to the power a cos theta by t, which is Gibbs-Boltzmann. So I think we stopped at that. And now the question is, how do I use this equation to find an expression for the stationary distribution of this system? So that is almost obvious, because you have to just compare this and that. So this I can write it as, in terms of this r and theta, I can write this as rt sin psi t. The same way we had dealt with the Bayer-Kuramoto model. Okay. And then we say that when we are in the stationary state, you can set psi to 0. And so this becomes omega I minus kr sin theta I, which is exactly of that form. So therefore, for this system, the stationary distribution will be, so let me just write it here. Yeah, can somebody tell me what is the modification that I need to do here so that it applies to this system? First of all, I need to define this quantity the way we defined it for the Bayer-Kuramoto model. That is, we look at group of oscillators with the same frequency, and then we ask, out of those oscillators that have the same frequency, what's the fraction that have the phase theta at time t, and when you are in the stationary state, what is the fraction of oscillators with frequency omega that have the phase theta in the stationary state. So what do I need to do here to apply this to that? What is the modification that I need to do? So I just need to replace this guy by kr. It's exactly the same philosophy that we had adopted while dealing with the Bayer-Kuramoto model, the one which does not involve noise. And how do I, now what do I need to do? What is R? Yeah, what is R? How do I determine R? Yes, exactly. So we did do the same thing, that is R, well, psi we have already put equal to 0. So therefore, in the stationary state, R will be d theta d omega g omega e to the I theta of rho ss theta omega. But again, there will be a real part and an imaginary part, and you can check easily by using the same kind of properties that we had used for the Bayer-Kuramoto model, that the sin theta component, that is the imaginary component, is 0, which is consistent because the left hand side is a real quantity. So therefore, I can just replace it by cos theta. How many of you are with me Or let's say how many of you are not with me? You are not with me. Okay. So let's see, where did I leave you behind? This one? This one, how do I get it? The modification. Okay, fine. Okay, see, the modification is this one. So first of all, you understand that for this equation, the stationary state is this guy with A appearing here, right? I mean, this should be A, okay? So let me see. So here it's an A and an A and an A. Okay? But now what I do is that this is for one oscillator, a single oscillator. I compare this equation with the equation that I have for the Kuramoto model. What is the equation? The equation is d theta I dt is equal to omega I. I am in the sorry. I am in the stationary state. So R and psi have attained time independent value. Okay, so I don't need to put a time tag here and neither there. Okay, so what I do is that it would be k of R sin psi minus theta I plus eta I. Now psi has become time independent, so what I can do is that I can rotate my theta axis and set psi to 0. That is to say that sine of psi minus theta I, it now looks like minus sin theta I, right? Because if I set this to 0, sine of minus theta is minus. So this equation, it looks like minus k of R. R is time independent, sin theta I plus eta I. Okay? So this equation there, it has the same mathematical structure as this one. If I replace A by KR, this is for the ith oscillator and this is for a single oscillator. So therefore what I do is that I take the solution for this, this system, which is this, and replace A by KR, because that's an exact identification, no approximation. That's what I did there. Okay? But then R has to be determined self-consistently because I don't know what R is. So what I do is that R is of course determined in terms of the stationary distribution by the following formula. R is equal to d theta d omega g omega rho stationary theta omega times e to the I theta. Now e to the I theta, there will be a cosine part and a sine part. The sine part will just evaluate to 0. You just plug this in or just look at the symmetry. The same kind of symmetry that we had used for the Bayer-Kuramoto model. G omega is equal to G minus omega and rho stationary. Theta plus pi is equal to rho stationary, I guess theta omega, something like that. Okay, so you can just check. Then the same symmetries will apply here. So the real part will be retained and the imaginary part will just go away, which is consistent because the left hand side also is a real quantity. So therefore it is consistent that this one is non-zero. Yeah, yeah, sure.
About the stationary state, I think we use the fact that we want to fix to some value the current, but I don't see any current in the...
Yes, it will be contained here.
Okay.
Yeah, because this is a constant, it has to be fixed by the normalization. Because this is a constant that depends on the frequency, so it has to be fixed by normalization. Okay, so now the rest of the game is, I think, exactly identical to what we had done for the, how we had played the game for the Bayer-Kuramoto model. So what you do is that you take the stationary distribution, you plug this in here, and try to solve for R self-consistently. If you do that, the first thing that you notice is that R equal to 0 is always a solution, as was the case for the Bayer-Kuramoto model, that so let us see. So suppose you put R equal to 0, that is the unsynchronized solution. Okay. So how does R stationary theta omega look like? So what I need to do is I need to put r equal to 0. So this guy will be e to the power, let me see, e to the power omega theta by d, and then you have this guy 1 plus e to the power minus twice by omega by d minus 1. This would be e to the power minus omega theta prime by d because r is 0. So this integral will be e to the power minus omega theta prime by d 0 to theta. So if you do it, you get what? 1 minus e to the power 1 minus e to the power minus omega theta by d. So I am just solving for the stationary distribution when the system is in the unsynchronized phase. So I just put r equal to 0 and I am just evaluating these two integrals. So this guy will give me the factor here and this guy will give me the factor there. Okay? And you see that these two, they would cancel excepting for a minus sign that you pick up here. So this term will evaluate to what? It would be e to the power minus omega theta by d. Somehow I messed up something. No, it's okay. Fine. So therefore, if you combine these two, this will cancel with that. So you just get a omega, which you fix by normalization. So you get this is equal to 2 pi. So this is exactly what you should have gotten because this is an unsynchronized state. So the phases, the phase points are uniformly distributed between 0 and 2 pi. So you should have gotten 1 by 2 pi and that is exactly what you get. I guess this calculation is okay, right? What I did was I just put omega r equal to 0 and just evaluated those integrals. So there will be a massive cancellation. All these terms, they cancel away and you get a e to the omega theta by d to the power minus omega theta by d. So you get a 1 factor from this. So you just get a omega, which you fix by normalization. You get 1 by 2 pi. So r equal to 0 is fine. So r equal to 0, consistently you get r stationary theta omega equal to 1 by 2 pi. Now we have to look for a solution r not equal to 0. And for r not equal to 0, again, what you need to do is you look at the r equation. Sorry, I just rubbed it off. So what I need to do is I need to plug this in here, and what I want to see is if I approach r equal to 0 from the right hand side, that is if I take the limit r going to 0 plus of this equation, then what is the critical value that I get? That would give me the value of the critical coupling. Okay, you get the picture, right? So what I have is I have a Kc, I have an r here and a k here and a Kcd here. Okay, this is this, and what I want to do is I want to approach r equal to 0 from the right to see what is the critical value of coupling that I get, and that would give me the critical coupling beyond which the system shows synchrony. So this calculation is slightly non-trivial but not too much, but still let me just spell out the main steps and leave it at that. Okay, so let me first write down the equation. So I have d theta, sorry, I write it this way, d omega g omega. I'm writing it in full glory, so therefore what I want to do is I want to study the right hand side as r goes to 0. You see rho stationary theta omega, it depends explicitly on r. R is sitting everywhere, upstairs, downstairs, everywhere. So when I do r going to 0, what I can do is that this depends explicitly on r. So I can do a Taylor expansion of this guy because I'm looking at the limit r going to 0 plus. So what I'll do is I'll Taylor expand this guy in terms of r, like about r equal to 0, and retain lowest order term to see if I get a non-zero value of the, what is the non-zero value of critical coupling that I get. So if I do this Taylor expansion, so I get this. So what is the first term that I should get when r, when I Taylor expand about r equal to 0, what is the first term that I should get? 1 over 2 pi. 1 over 2 pi plus r of del rho SS theta omega del r going to 0 plus higher order terms which I neglect. So these things can be done explicitly, obviously, because you know rho stationary theta omega, so you can do this. So it's all spelled out in the notes. How does this guy look like? So I'm just skipping the details because it's a simple exercise to take that expression and take the derivative with respect to r. So if you do all these things, the final answer that comes out is, so if you do this, you see there is an already factor of r appearing here. So, and r is non-zero. The first term will cancel out. Why? The first term will give me 0, this term. It won't matter. Why? Can somebody tell me why this integral is 0? Yes, exactly. So this term goes away. So the leading term is of order r, which is exactly what I want. I want to cancel this r. Because r is non-zero, I can cancel. So the leading term is already of order r. So I have to just do this derivative. If I do that, the final answer that I get is okay, let's write it KCD. Something like that. And if you simplify this, then what you get is you get your critical coupling to solve this equation. Get your critical coupling to solve Kc is equal to 2 divided by Kcd. 2 divided by minus infinity to plus infinity of g omega d omega of d divided by d square plus omega square. So this is the equation of that line that I had drawn. This is Kc when d is equal to 0. So this is 0. So this thing is the equation of this line. Can one quickly check that when d goes to 0, then I recover Kc d going to 0 is equal to 2 by pi g0? Can one quickly check this? What do I need to do? What happens when d goes to 0? What does this guy give you? Yeah, it would be a delta function. So exactly. So your delta function evaluated at 0 because this will be 0 unless omega is 0. Okay. So then you get exactly this one. Just take the definition of the delta function, or you can do it also. It's quite easy to do. Okay. So we are all in good shape, I hope. that we have been able to recover the bare Kuramoto model answer and have been able to go beyond in getting the value of the critical coupling also when there is Gaussian white noise in the system. Now you may wonder, before I move on, like are there questions on, see these calculations are trivial, so they are all worked out. So just let me know if you get the philosophy, what is it that we are trying to do, and whether you get the big picture. I mean, this integration, maybe there's a factor of half missing here and 2 appearing there, but those can be fixed. Those are simple things. The main thing is to know what is the thing, what is the, the big picture that we are trying to address. So I hope that is clear, right? Or if not, then just let me know before I go on to discuss something slightly off the track. Huh? Which one? Yeah. So what you have to do is you have to take the derivative of that beast that I had written down, and when you take the derivative, you get all the cosine square and sine square and cosine and sine and so on. Yes, so the cosine square and sine square, those terms will survive. Cosine, sine, they will just go away. And so you ultimately get this one. It's all worked out in the notes, but you have to just be patient and carefully take the derivative of that rho stationary theta omega with respect to r. So I think the main takeaway message, Sorry? Yeah. What, sorry? Yeah. Synchronization, you are synchronized here, no? So the phase diagram that I have is this one. That, or maybe it is here also. So on this side, the system is what? Can somebody help me? This side? Synchronized, right? So this is r not equal to 0. And on this part, it is unsynchronized, r equal to 0. Right? So this is the picture. So when d was equal to 0, sorry, I did something, sorry. I'm sorry, it should be d. So KCD is this line. So when d was equal to 0, the critical point was here. So the system was unsynchronized here and synchronized there. When you introduce d, the region of unsynchronized phase expanded. Now you have a bigger region in which compared to d equal to, so d equal to 0, only this much region, this much parameter regime for k was unsynchronized, and as you increase d, you get a wider region over which the system is unsynchronized, which is expected because you are adding noise into the system, and the noise is uncorrelated between the oscillators. So every oscillator is getting an independent kick or experiencing an independent noise. So therefore, it's no surprise that the system would like to remain unsynchronized for even larger value of k. So you need the coupling to be even more strong than the case when there was no noise in order that the system gets synchronized, which is exactly happening, what is happening here. This line is shifting to the right. The point is shifting to the right. Huh.
Where does this factor of pi come from?
Oh, it comes from the definition of delta function. Yeah, because delta function, if you write, so look up, so delta function has several representation. One is of course in terms of e to the I, this one, but this one also, if you look up the definition, it just comes from there. See, delta function can be defined in terms of a Lorentzian. So why does this factor come in? Because you can think of delta function as the limit in which a Lorentzian distribution, the width of the Lorentzian distribution is shrinking to 0. And what should happen when the width of a Lorentzian distribution shrinks to 0? Then what should happen? I mean, can I just take a Lorentzian and just squeeze it to 0? I cannot, right? I have to do something, I have to conserve something. Normalization, so therefore the peak increases. So which is exactly the form of a delta function, that this guy, it just compresses in this direction, so it shoots up in the vertical direction. And in the definition of a Lorentzian distribution, there is a pi factor, a sigma by pi 1 by sigma square plus omega square. So that's why you get this thing there. This is sigma by pi is not there, and sigma square plus omega square, so you put in a pi and so on. Okay. Are there other questions?
Yes, what do you mean by R different from this state?
R different from 0, sorry, oh gosh. There is no gamma. This part is synchronized, this is unsynchronized. So I guess the main takeaway message is that when you have a system, why we could do all this analysis? We could do all this analysis simply because we were able to write down the equation of motion of the phase variables, or whatever was the dynamical evolution equation, we could write them down in terms of the order parameter, right? So we had n coupled entities. So let me just spend 2 minutes on this. You know, this kind of technique of writing solving for the system in terms of a single particle dynamics, it applies not just to Kuramoto model or to Ising model, but to any models for which you have an equation of motion which is of the following sort. Let's say this is the dynamical variable, and if you have if this guy is, it may be written down in a form such that there is a coupling between all to all the xi's are coupled with equal coupling. So let's say you have a form which is like this. Let's say j is equal to 1 to n of some function of xi xj. Okay, if you have a dynamics of this sort, then, and you see the coupling is the same. Like had I had a factor here which is, let's say, aij, then of course still, I mean, everyone is coupled to everyone else, but then not equally well, okay, because this aij is determining the coupling between the ith and the jth guy. More generally, this function also may depend on the ith and the jth entities, but if these dependence is not there, and if the coupling is the same for all, that is, you know, this is just a constant that I can pull out, then if I define a suitable order parameter, something that characterizes the system on a macro scale, I am able to write this down in terms of a set of apparently apparently uncoupled equations. Some order parameter that I write down times some gxi. And once I do that, then my life becomes simple. Then I may pretend as though the different dynamical variables are not interacting with one another, solve for the xi's and put that solution back into the definition of R and solve that equation self-consistently. This is routinely done in many statistical and nonlinear dynamical systems models like Ising model, Heisenberg, mean field Heisenberg, Curie-Weiss model, this, that, etc. The philosophy was okay, right? I mean, what I... Okay, so before we go to other aspects of the Kuramoto model, you may wonder, what about the Orth-Antonsen answers? What Orth-Antonsen answers allowed me is to write down a single equation for the time evolution of the order parameter. Can I do the same thing when I have noise in the system? Like, am I like able to write down an equation for drtt? If you recall, for the Bayer-Kuramoto model, it was something like this: r square. Actually, I don't remember what does it look like. Let's see. Not that it matters, but still. Yeah. So it was sigma r plus k by 2 of r cube minus r equal to 0. See, this was the time evolution equation that we had written down for the order parameter in the Bayer-Kuramoto model. Now you may wonder, if I can write down a similar equation also when there is noise, and do I get something like this? This would be the best guess, right? Because when eta is 0, I recover the usual Kuramoto model Authantonsson answer, and I just put a noise here. Am I able to do that? The answer is no, because here all those nice properties that there is a manifold to which the solution is if you start on that manifold, you remain on that manifold, etc., they don't work. So therefore you don't have an Authantonsson answers when you have noise in the dynamics. So you cannot write down an exact equation, time evolution equation for the order parameter when you have noise in the system. Which is not so surprised, because when you have noise, then things may go, may get modified significantly enough that the arguments that you had put forward for the deterministic system do not straightforwardly generalize when you have noise in the system. Okay, so there is no such thing here. Achha, one more limit I forgot to mention, so let me just mention it, the equilibrium limit. Equilibrium limit is when all the frequencies are the same. Okay? So then this rho stationary theta omega would be just e to the power, it's really very simple, e to the power kr cos theta by d. Right? This is the equilibrium limit when there is no frequency. The frequency term is 0 for all. Okay? So then this divided by the normalization, which would be the, so there is no, now I don't have to worry about omega. So this is the equilibrium one. So this is the canonical equilibrium distribution for the system in contact with a heat bath at temperature T. So this is the canonical partition function. And for this one, if you now compute R, which will be, do I need to do an integral over omega now? Do I need to do any integral over omega now in the definition of R? No, because there is no omega. The frequency term has been set equal to 0. So therefore, you can just plug this in here, and you can find that this is given by the ratio of two modified Bessel functions. Okay, this is I1. So these are the modified Bessel function. Okay, so the definition is INX. Sorry. And in this case, you can find out the critical coupling beyond which the system is synchronized. I think it is T by 2. Yeah, I think it is T, which is T by 2. This is the answer that some of you may recollect from your solution of the XY spin. Take a collection of XY spins, all-to-all coupling, and the system is in canonical equilibrium at temperature T. What is the temperature beyond which the system is? You don't say for the XY spins the word synchronization. You say that the system is what? For XY spins, what is the natural terminology that one uses? Huh? Pressure? No. Phase? No, phase separation. It doesn't show any first order transition. Magnetization. Right? For xy spins, you would talk about magnetization. So this is the critical coupling beyond which the system is magnetized, below which the system is unmagnetized. There is no synchronization here because it's not that the phases have a frequency and so on. Yeah. Is there a question? Yeah.
Why did we put the value of Kc equal to the AT over 2?
Oh, you just, what you do is that you do the same game. Okay, this is the self-consistent equation. What you do is that you first of all you see that if r equal to 0, it is always a solution. Okay, second one is that you look at the right hand side and consider its limit as r goes to 0 plus. If you do that calculation, you get this critical coupling. So whenever you have a second order phase transition, this is a trick that you do. That when you are in a close to a second order phase transition, you are approaching the critical point from the side of the ordered phase, and you want to know what is the critical point, what is the value of the critical point. So you approach the critical point from the ordered phase. So for magnetization, of course, it is for example, you must have done it for Ising model and so on. No? This is a magnetization, this is temperature, this is critical temperature. You want to know this one. So what you do is that you write down the self-consistent equation and you evaluate its form when you approach the critical point from the ordered phase. When m goes to 0 plus, that is the magnetization is 0 but not quite. It is very close to 0. That's how you get the critical temperature. So I want to now talk about something slightly different, and from maybe tomorrow half the class maybe I'll start talking about the quantum dynamics. What does it mean to have synchronization in the quantum setting? But before that I want to finish off with something still in the classical regime, which is the fluctuation theorems. So I'll state what they are and then I'll show how you can demonstrate their validity in the context of the Kuramoto model and what all you can infer from such a. So no more questions, I guess, on the yes. Yeah.
Way of approaching the model captures the scenario where we have two exact opposite clusters of oscillators, for example, because I remember that in the Ising model with neutral you cannot capture the anti-ferro. Is it the same in this model, or do we have any trick to kind of?
No, first of all, in Ising model, in which Ising model? The mean field Ising model, the mean field approximation will give you the right result. If you take the Curie-Weiss model, which is this guy, you get the right critical point, because this is again all-to-all coupling. So mean field approximation is exact, it is not an approximation. So like again, this is already given in terms of the order parameter, because this is just m square. M is the magnetization. I can write this down in terms of the magnetization. This is the magnetization of the Ising model. So I guess this is minus j m square by 2. J n m square by 2. So this one will give you where in the case of Ising model, where does the mean field approximation go wrong if you try to solve it for this case, where the coupling is not all to all but between nearest neighbors. Here if you apply mean field approximation, then you get a wrong critical point, because you get the critical point Tc, I guess it is KBTC is 2j by z, I think. This is the right dimension, I think it is correct. Okay. So you get the wrong critical exponent because it seems to predict that when you are in 1D you get a phase transition at a non-zero temperature. For 1D z will be the coordination number, so it is 2 in 1D. So here you go wrong because anyways this is not all-to-all coupling, so you are doing an approximation, but here there is no problem. By the way, can somebody make a guess, like why do I, whenever there is global coupling in the system, I tend to put an n here? Or okay, let me backtrack a little bit. So let's say, what happens when I do this Kuramoto model, but not all-to-all coupling? Instead, the case in which there is interaction only between nearest neighbors. So first of all, what I need to do is that in order that I can define sensibly nearest neighbors, I have to put the system on a lattice, right? I cannot have all-to-all coupling. All-to-all coupling means that there is effectively no underlying lattice structure. So what I do is that I put them on a lattice. So the best thing to do, or the simplest thing to do, is to put them on a 1D lattice. So at every lattice site, there is an oscillator, theta I, and this equation will look like what? Can somebody help me? How does the nearest neighbor Ising model on nearest neighbor Kuramoto model on a 1D lattice, how does the equation of motion look like? How would the equation of motion look like? K, yes? Yeah, so you can, something like this, right? Ij. You see that whenever there is global coupling, I tend to put an n factor. For the Ising model, for the Kuramoto model, when I had global coupling, the second term looked like k by n. Okay, whenever there was global coupling, I tend to put an n factor here as well as here. But when I have local coupling, local meaning not all to all, then I seem to be happily forgetting about putting that factor n. Neither is a factor of n here, nor is it there. Why is it? Why do I do it? Of course, you can say that I do it because I can solve the model, but that is not the. Maybe I don't need to also solve the model at times, but still I should be happy with the physics of it. So can you guess why I need to put an n factor here? What does it do basically if I put an n factor or if I don't put an n factor? Certainly as far as the counting part is like concerned, then I am in good shape because I tend to count every pair twice, so that's why I put a 2 factor, that's okay. But what about this n factor? Why do I put it? Yes, extensive, because what happens is that if you don't have this n factor, then what will happen is that your energy will scale as n square. Huh? This you see because SI is a number of order 1. So there are how many SIs? N square number of SIs. So this, without the n factor, the energy will scale super extensively with the energy. But so what? I want to make it extensive. Why do I want to make it extensive? Here also, sine is a term it cannot exceed 1. It lies between -1 and 1. So therefore, when I am adding the contribution due to nearest neighbors, it's of order 1, doesn't matter. But when I am adding contribution due to all my, all my friends and foes, then there are n of them. So this term, the summation itself is of order n. So I need to divide by n here, or if you write down the corresponding potential term, I need to put a n factor there. Yeah. Why do I want to make it extensive? Any guess? I mean, why would I like to have a statistical mechanical system? I have noise now. I mean, why do I want to make it extensive? Huh? Yeah, in some sense you are right, it doesn't depend on the size of the system, but also what I want is that I want some effective competition between the two terms. You see, if I don't put an n factor here, then what will happen is that this term scales as n. So as I make n larger and larger, the second term will happily dominate over the first term. So the first term will be effectively not so important. Okay, this is one way to rationalize why do I need a factor of n here. Extensivity. Extensivity one can motivate in another way, which is the following, that let's say I am doing the equilibrium statistical mechanics of this model. So what I would like to do is, let's say when the system is in canonical equilibrium at temperature T, then what I would like to do is to find out the minimum of the Helmholtz free energy, which is U minus Ts. So how many of you are familiar with this expression? This is the Helmholtz free energy of a statistical mechanical system, thermodynamics. Okay, this is U is what? U is the internal energy, which is the average of H. S is the entropy, T is the temperature. Now the thing is that if your energy scales super linearly, that is if you have a term which is not extensive but super extensive, while entropy is a term which is always extensive. Why? Because entropy doesn't care about whether the system has long range or short range interaction. I mean, whether there is all to all coupling or whether you have nearest neighbor coupling, it doesn't care. Because entropy has to do with counting. It has to do with how many ways you can distribute, what is the number of consistent microstates, kb log gamma. So this term would scale as n, while if this term scales as n square, then I am in deep trouble, because then when I try to minimize the free energy, I need to minimize the free energy to get to the equilibrium state of the system. If I need to minimize the free energy, I may as well forget the contribution of the entropy, because this is a subdominant contribution. So therefore minimization of free energy is as good as minimization of the energy itself. And why is that a bad thing to do? I mean, why minimization of free energy when it becomes equivalent to minimization of the energy of the system? Then I say that it's a boring thing to do, because there's nothing left in it. In the classical setting. In the quantum setting, it picks up some extra dimension. But in the classical setting, I hope the question is clear, that I have a set of entities and they are interacting with one another, but the interaction is such that the interaction energy scales super linearly with the number of particles. And when I keep this box of particles in contact with a heat bath and I ask, what is the equilibrium configuration, what is the, how do the particles distribute themselves in equilibrium, I say that if the interaction is super linear, then it's a boring thing to do. There's nothing left to do. I mean, the problem is almost solved. Why is it so? Any guess? Just from basic thermodynamics. I mean, you don't need Kuramoto model. You see, when the entropy term is subdominant, then you just minimize the energy. That means you just look at the ground state of the system. You don't have fluctuations. There is no fluctuation. You are in the ground state. It's a classical system. Even the ground state doesn't have any fluctuation. So you just find out what is the configuration that minimizes the energy of the system, and you just remain there. That's it. Okay? The higher energy levels are not at all accessible to you, because you don't even get there. You just go to the ground state and that's it. Okay? For example, that's what happens for the Ising model when you are exactly at 0 temperature. The ground state is very boring. It's the one in which all the spins are up, and that's it. There's nothing more to do. What else can you do? Because there is no entropy. The problem, the interesting thing happens when you increase the temperature. Then you have many configurations, because you can go between configurations. So you have one in which this spin is up and the rest of the spins are down, or maybe some fluctuation here, there, etc. So this is one reason you would like to have the energy to be extensive in n, because otherwise you don't have a competition between energy and entropy. And so minimization of free energy is as good as minimization of energy. And so therefore things become very boring. There's nothing left. In the quantum case it is good, because in the quantum case when you are at 0 temperature, even the ground state will have fluctuations, quantum fluctuations, because you cannot say for sure that the system is in the ground state, meaning the state of the system is exactly this. You know, when you make a measurement, you may get this value or that value or this value or that value, etc. So therefore you have inherent quantum fluctuations. Okay, so much for the classical one. Let me just, I hope this is clear, right? Somewhat. It requires to read up, it requires you to read up some basic literature on books on thermodynamics. Okay. Now I want to talk a little bit about stochastic thermodynamics, because you can, as I mentioned, you can demonstrate the validity of a large number of results there in the context of the Kuramoto model by using the Kuramoto model. Okay, so what is the thing that, so I will talk about two particular theorems. So let me first, so let's say this is your system. So for the moment you forget about Kuramoto model, you think of some system, a system of particles. It could be 1 particle, 50 particles, 5,000 particles, whatever. Okay, so this is my system, and this is in contact with a heat bath at temperature T. So what does the heat bath do? The heat bath maintains the system temperature to remain fixed at the value T. So there is always this contact with the heat bath, and therefore the temperature of the system remains fixed at temperature T. Now let's say that I write down the Hamiltonian of the system, and so the Hamiltonian of the system, so there are many particles here and whatever and whatever. Okay, so let me use the letter X to denote a microstate of the system. So what could be the microstate if I consider the let's say a gas of particles? What would be the microstate? The position and the momenta, right? And for the Kuramoto model, it would be what? Theta I. And let us say, so let me write down the Hamiltonian of the system. The Hamiltonian will obviously be a function of the microstate of the system. You see, I am using the same notation. And let us say that in the Hamiltonian there is a parameter lambda. So let's see what sort of parameter I can think of. For example, let's take the Kuramoto model, because then life will, it's not a Hamiltonian system, but okay. I mean, for the Kuramoto model, I have to define it differently. But let's say I look at the Kuramoto model in which all the frequencies are the same. They are not there. I mean, the frequency is not the same. They are not there. That is to say that the equation of motion is this sort. d theta I dt is equal to k by n sine of theta j minus theta I. This we saw models an equilibrium system, right? For this, the equilibrium distribution is e to the beta h and so on, right? So what will be the Hamiltonian of the system? It is the potential energy only. This would be, this we had written down several times. So but I am claiming that there is another parameter in the system which I can tune as a function of time. Can one think of how how one may add a parameter to this Hamiltonian that I can change as a function of time. Coupling, presumably I cannot change as a function of time, presumably, because coupling is given to me. I am given a set of particles and they are interacting with one another with a coupling that is given to me. How do I introduce a parameter that I can change as a function of time in this setting? Natural parameter that an experimentalist will think of. So these are x-pi spins, right? We talked about them, that these are x-pi spins and this is the x-pi interaction. So what is a parameter, what is a natural parameter that an experimentalist would apply to the system? What is the thing that he or she would use to tune in time or do some experiment with it? And in fact, this is the way in which he gathers information about the system. Magnetic field. So what he would do is that he would take this model and then he would add a magnetic field to the system. So the magnetic field couples with, let's say the magnetic field is in the x direction, so the coupling will be like this. And what he can do is that he can make this magnetic field a time dependent function. You can change the magnetic field. Let's say he applies a periodic field, Fluke kind of Hamiltonian. So this lambda t is such a parameter that he can change as a function of time. And what we want to see is what happens when he changes it along a particular way, and what do I get. So let's do the following experiment. So the experiment is at time t equal to 0, lambda, this lambda function t equal to 0, it has got a particular value, let's say lambda 0, and what we do is that I first turn on the magnetic field, keep it fixed at a certain value, and let the system equilibrate at that value. Okay? So at lambda t equal to lambda 0, the system comes to canonical equilibrium. And then, lambda is equal to 0, so therefore what will be the stationary distribution, the canonical equilibrium distribution? Would be just e to the minus of h of x lambda 0 divided by t divided by the partition function, where z lambda is defined to be the partition function. Let me write it big. Where beta is 1 over kBt. So this is at t equal to 0. At t equal to 0, I turn on a constant magnetic field, time independent. I keep it fixed at that value. I let the system come to equilibrium, and the system is in contact with a heat bath. So therefore the system will attain canonical equilibrium. So therefore at that value of lambda 0, what is the equilibrium distribution? It is just e to the power beta h. Okay, let me write beta h more. Then what I do is that I start changing my lambda. Okay, so this is my lambda as a function of t, this is my t, this is 0. I started out from lambda 0, and then what I do is that I change it arbitrarily over some fixed time. Let me see, using t or t star. T, okay. You get the experiment. Now I am changing the magnetic field. But I don't say that I change the magnetic field infinitely slowly or infinitely fast or anything. What I do is that I just change it according to my will over a finite time interval 0 to t. Okay? So in doing so, it is not guaranteed that although I started out with the system in equilibrium, at these intermediate times the system is also in equilibrium. Why? Because what I did was I became very rude and aggressive, and so I started with the magnetic field value at 1 Tesla and then I suddenly made it 10 Tesla, okay, in 2 minutes. So I started from 1, the system is in equilibrium, and suddenly made it 10 Tesla in 2 minutes. Okay? So the system would not have enough time to get adjusted to the changed magnetic field. Okay? So therefore, although it started out with equilibrium, in these times when the magnetic field was changing, at these instances the system will not be in canonical equilibrium, it will be kicked out of the equilibrium. When would it remain in equilibrium? If I do this change very, very slowly. What do I need to do to make this change very, very slowly? That is, if I make this lambda change almost parallel to the x-axis, then I am changing very little. But I am not specializing to that special situation. I am saying that, okay, I start from this one and then there is a way in which I change it and it is my way. Okay? Then at time t, I stop the experiment. Okay? So at time t, let's say lambda has got the value. Let me see what is the notation. Oh, I am using lambda I and lambda f. Okay. So this is lambda I, lambda initial, and this is the value that I get to at time t, lambda f. So this is lambda I, lambda I, lambda I, lambda. So what I do is that at time t I stop the experiment in the sense that I no longer change the magnetic field any further. Okay? So then at this point the magnetic field remains constant and I keep it constant in time, and then eventually at some time t star it is remain constant. Okay? The system will come to a new equilibrium corresponding to this new value of new value of lambda. Is the experiment clear? So what I am doing in the experiment is, by changing the magnetic field, I am driving the system from one equilibrium state to another equilibrium state through intermediate states which are not in equilibrium. So this is quite unlike what you study in thermodynamics. When you in thermodynamics talk about thermodynamic transformations, you talk about quasi-static transformation, that the system is initially in equilibrium and you change your external parameters slowly and slowly, little by little, so that the system goes from one equilibrium state to another, to another, to another, to another, and in this way it goes from one equilibrium state to another through a number of intervening states which are all in equilibrium. Here I am doing something drastic. I am also going from one equilibrium state to another equilibrium state, but the intermediate states do not have to be in equilibrium. In fact, they could be anything but equilibrium, because I decided to change lambda arbitrarily in time.
What is the definition of the magnetic field in this case?
Achha. So this lambda is like the magnetic field. So it is any parameter in the Hamiltonian that I can tune as a function of time. Okay? For example, for this XY spin model, it could be magnetic field. But let's say for the gas contained in a chamber, and the piston is something that I move. So this lambda could be the position of the piston.
Yes, but there is no precise mathematical expression, just any parameter.
Any parameter that appears in the Hamiltonian that you can tune, any dynamical parameter that appears in the Hamiltonian. Let's say here in the case of interacting particles, coupling maybe is not the right thing to tune, but let's say you have a particle contained in a harmonic potential. So what I can do is that I can change the trapping constant, that is I can make the the stiffness constant, not the trapping constant, the stiffness constant, that is to say that I can make the particles more trapped or less trapped. So I start with the particle in a harmonic potential at this value of the stiffness constant, and then suddenly I make it like this. And the question is, what happens to the system? Okay. So let's say I start with the particle in a harmonic potential which is of this sort at t equal to 0, and then suddenly I make it like this. Suddenly, if I slowly make it, if I slowly open up the potential, so the system was initially in equilibrium, and then I am slowly opening up the potential, the system will continue to remain in equilibrium at all times. And then I will ask, how does the, what is the thermodynamics of the system as I go from this equilibrium state through a series of equilibrium states to a new equilibrium state. I am not asking that thing, I am asking more a more drastic question, that is I start from here and suddenly make it like this. Okay.
Sorry, the last question, just to understand. So if we take all our frequencies equal to 0, we can do an approximation as a Hamiltonian.
Yes. In fact, you may ask what happens if I do this experiment with the frequencies put in. Okay? That I will explain, of course. I mean, there you cannot write down a Hamiltonian, but there is an equivalent formalism. But I think the Hamiltonian formalism is easier to understand, and historically it was also the first one to be proposed. So that's why I thought that I first deal with the Hamiltonian case and then go to the non-Hamiltonian case, the Kuramoto model in full glory. So I will first start with the xy one. The xy one, there is a magnetic field that I change as a function of time, and I do this. Okay. So you see, what I am doing is that in this part of the dynamics, when I am changing lambda as a function of time, lambda is the parameter that I am tuning, magnetic field or the stiffness constant of the harmonic potential or whatever. What I am doing is that in this part, I am pumping energy into the system, I am doing work on the system. Why I am doing work on the system? So that is quite easy to see. Well, work can be done on the system or by the system, depends on my, the situation. But let's see, why do I do work on the system? Because let's take the situation of a harmonic potential, and let's take a single particle. So this is my harmonic potential, half kx square as a function of x. Okay. So first what I do is that I keep my k fixed. Okay. Let's say k is equal to k0. Okay. And I let the system come to equilibrium. So if it comes to equilibrium, then the particle will most likely be where? In equilibrium? Here, right? So the probability distribution will be somewhat like this. This is the probability distribution rho equilibrium. I am using the same notation, x comma k0. Okay. So this is the probability distribution. Most likely it will be at the center of the potential, but there are smaller probabilities of finding the particle also away from the potential. Okay. So let's say the particle is here at this location. At a, when I am doing the experiment at a given instant in the stationary state, let's say the particle is here at, let's say at t equal to 0, and then suddenly I make the potential, let me draw it here because then it will be like easier to. So there is a good chance that the probability the particle could be here, no? The probability is small, but still it is not 0. Okay. And then suddenly I make the potential more flat. The particle was here at t equal to 0 in equilibrium, of course. This is an equilibrium, this is a possible equilibrium position of the particle. And then suddenly, let's say I make the potential more flat, more shallow. Then what the particle will find is that its potential energy has changed suddenly by this amount, right? Because this will be the change in the potential energy. Where would it get this energy from? It would get it from the source that is changing the stiffness of the potential, because it suddenly finds a different potential. So therefore, in technical terms, what you say is that the source which is changing the potential is doing some work on the system, and that work that he is doing is getting converted into energy, change in energy of the system. So therefore, what will be the work done? The work done will be, in this setting, how much does the energy change when lambda changes by a small amount, d lambda. And this energy change, this work done takes place all the while from 0 to t. So therefore, this guy will be Is this definition clear? This is the work done on the system. Because what this guy tells me is how much does the Hamiltonian change when lambda changes by a small amount, and how much does lambda change? This is this d lambda, which is nothing but lambda dot dt, and I need to integrate over the time from 0 to t, because this is the regime in which lambda is changing, this is the regime in which lambda is not changing. So if I evaluate the integral in this part of the protocol, then there is no change in the in the integrand, and therefore W will evaluate to 0. Is this okay? So what thermodynamics tells me is that traditional thermodynamics. So there are two energy scales that I need to compare with. Okay? So one is the following. One is, of course, what is the total work done on the system, that is this guy. The second one is I am going from one equilibrium state to another. Okay? So therefore, I should talk about what is the free energy difference between these two equilibrium states. How do I define the free energy? Free energy is defined the way it is defined in statistical mechanics, that the free energy when when lambda has got the value this, it is equal to minus kBt log of z lambda. So what I do is that when lambda is fixed and the system has attained equilibrium, I find out the canonical equilibrium distribution, which is e to the minus beta h. I compute the partition function and I take the log of it, multiply by minus kBt, this is the free energy. So therefore, what is this delta f? Delta f is equal to the free energy at the value lambda f minus the free energy at the value lambda I. Is the definition clear? W and delta f. Delta f is the free energy difference between the initial and the terminal equilibrium state. There are two equilibrium states. This is one energy scale and this is the. So what thermodynamics tells me is that if I do this change quasi-statically and reversibly, that is to say that I do it very, very slowly, infinitely slowly in time, okay, then can you tell me how does this work compare with delta f? This is a statement of this, this is a consequence of the second law of thermodynamics encoded in what is known as the Clausius's inequality. Clausius's inequality tells me that W and delta f, these are related to one another in some way. What is the way? When the change is done infinitely slowly, that is I change lambda very, 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 very slowly, and then still I go from one equilibrium state to another. So this is maybe a second class of thermodynamics, that in the second class of thermodynamics that you learn about how do these two quantities compare with one another. What I should put here? Yeah, so if it is infinitely slowly, then this is equal. While If it is not done infinitely slowly, that is if I do it drastically like the way that I did it here, I did not do it infinitely slowly, I did it according to my wish. So then this becomes greater, because the amount of work that goes into the system is higher than the change in the free energy of the system between its two terminal equilibrium states. This is a consequence of the second law of thermodynamics. Okay? And second law of thermodynamics, as you know, it can be stated in many different ways, but simply put, you cannot absorb all heat from a reservoir and convert it fully into work without doing anything else anywhere in the atmosphere. In the universe, you have to do something. You cannot have a perpetual machine, engine. So this is what thermodynamics tells me in this setup. But you see, thermodynamics has an essential ingredient contained in its very formalism. That is to say, in thermodynamics you always deal with thermodynamic system, namely a system that comprises a very large number of interacting particles, typically of the order of Avogadro number. Okay? But suppose I had done this experiment just for fun. Let's say I had done this experiment not for a thermodynamic system, but for a single degree of freedom. Eventually what I will get to is, you see, in our Kuramoto setup we have already seen two extreme cases, one in which I have many entities, many oscillators, and the other in which I had just a single oscillator. Non-uniform oscillator, right? So suppose I do this experiment for the Kuramoto model, in which all the frequencies are set equal to 0 and there is a magnetic field that I change as a function of time from 0 to t, and I go from one equilibrium state to another, and I measure delta F and I measure W. I can check that this equation will hold. But suppose I had done this not for this many particle system, but suppose I had done it for a single oscillator. A single, I can, I drew this picture of my system comprising many particles in contact with a heat bath. But if I do it for a single oscillator or a single degree of freedom, it would be fair to say that perhaps I will, this equation will hold only on its average. Okay? So because W itself will be a fluctuating quantity, so therefore if I have a single degree of freedom, then all those law of large numbers etc. will not hold. So therefore instead of talking about W, which will now be a random variable fluctuating a lot between, so what is this average? So let me first explain this average, what this average means, because then you will see why there is this law of large numbers coming into picture. So this average is the following. So I do this experiment over and over again, in each of which I start the system in equilibrium here and I let the system evolve under a time dependent lambda, and the lambda dependence in time, it is always the same. That is, in each experimental run, lambda always changes the same way. But what is different from one experimental run to another is the fact that the system is evolving in contact with a heat path. So therefore the dynamics is not deterministic but instead stochastic. So therefore if I repeat this experiment many times, what I am eventually going to get is a histogram for the W. It would have some form. And what I am saying is that the second law of thermodynamics, or the Clausius's inequality in such a setting, will apply not to any individual W but to the average of that probability distribution. So this angular brackets, it just means this guy, rho W, W dW. Is this picture clear? Because it is very important that you understand when you do this average, what are the things that you don't change and what are the things that you do change. So what are the things that you don't change? In every experimental run, you start from time 0 and you go up to time t. You don't change, you don't tamper with this value of t. Okay, maybe this t is confusing with that t, that is the temperature and this is the time, so maybe make it like this. Okay, tau. Okay. So this you don't tamper with, Also, the way you change lambda from lambda I to lambda f, this particular path of lambda also you don't tamper with. You stick to the same way, you don't change your will when you do the experiment a second time. You say that I will change always lambda in the same manner. But then what is changing when I am doing this experiment over and over again is the fact that the dynamics of the system, the degrees of freedom of the system that is taking place in contact with the heat bath, and I don't have control over the degrees of freedom of the heat bath. So every time I do the experiment, I'll get a different value of W. That is to say that I will end up with a probability distribution of W. And so therefore, this second law of thermodynamics, it would hold when I apply this to the average. And when I have many degrees of freedom, then you can easily convince yourself that this probability distribution will be largely a delta function. There won't be much difference between doing the experiment once and twice and thrice and for the fourth time. So therefore, if the probability distribution is a delta function, talking about the mean and the quantity itself means the same. Okay? Is this setting clear? What is the thing that you are changing and not changing and so on? So it is clear? You have to say, because otherwise how do I know? But the question is, this is an inequality. Can I turn it into an equality? Because equalities are always, good looking and they are better to deal with than. So it turns out that although this is an inequality, if I exponentiate both sides, okay? Suppose I look at this guy. And also I exponentiate this guy. So this becomes an equality. So it's a magic that although, at the level of quantities themselves, they have an inequality, but when I exponentiate them, they become an equality. So this equality, it is very famous in the literature, and it's called the Jarzynski equality. Sorry? Okay, this is, I'll prove it, it's a theorem. Okay? It is so at the moment I am stating the result, I did not give you the proof. But surely this one implies this one, surely this one doesn't imply this one. I can think of many probability distributions such that if I take its average and the average will be larger than delta f. So this one certainly doesn't imply that one. This you understand for sure, but this one certainly implies this one. So let's see how does it work. So that one uses what is known as the Jensen's inequality. It applies to any that applies to an exponential function in particular. Can you tell me of these two quantities, which one is the larger of the two? One is the average of the exponential of minus x. The other is the exponential of minus the average. Huh? Yeah. So this one is definitely larger than or equal to this, right? So therefore I just apply it there. So what I get is e to the minus beta delta f is equal to e to the power minus beta w average. But this one is larger than equal to e to the power minus beta w average. So now if I cancel beta and if I compare these two, take log or whatever, then you at once get is W average, this is greater means, which is exactly this one. You may have equality also. So therefore, definitely Jarzynski equality is consistent with the second law of thermodynamics, but second law of thermodynamics does not offhand tell you that this Jarzynski equality has to be true. Not just this, there is another theorem that was proved for this work distribution, which is the following. So here you see, before I go to that work distribution, let me just mention one more thing. That is that you see the left hand side, you would think would depend explicitly on how am I changing lambda as a function of time. Because this W, the function itself depended on how does lambda change as a function of time, no? Because there was this thing. This is the definition of W. So you may think that the left hand side, which is the average of exponential of this guy, it depends on the explicit form of the function lambda as a function of time. But it turns out that the left hand side doesn't depend on how do I change lambda as a function of time, which is quite good because I know that the right hand side doesn't depend on how does lambda change as a function of time. Why? Because free energy is a state function. Free energy depends just on the value of lambda. It doesn't depend on how does the system get there. So to compute delta F, what I need to do is I need to take the canonical equilibrium distribution, compute the partition function and take the log of it. It doesn't care about how does lambda change as a function of time. So the right hand side doesn't depend on the way lambda changed as a function of time, and so is the left hand side. That is one. Second interesting fact about this equality is that the left hand side is defined only up to this time interval 0 to tau, because beyond tau, that is between tau and tau star, W is 0. So therefore you compute it or you don't compute it, doesn't matter, because so there is no work done. So W, the quantity itself, is 0, while delta F, that is defined with respect to these two times, 0 and tau star. 0 is when the system was initially in equilibrium, and tau star is when the system is again in equilibrium. So therefore you have two sides of an equation referring to two apparently different situations. The left hand side refers to the time 0 to tau, the right hand side refers to the time 0 to tau star. And again, the left hand side in principle should depend on how lambda changes as a function of time, but the right hand side doesn't. That is one. And secondly, suppose I do this experiment in the following manner, that this is one way of doing the experiment, and this way of doing the experiment I get the histogram of W. But I can do this experiment also this way, that at time t equal to 0, the system was initially in equilibrium at lambda f, so this is lambda t as a function of time. The system was initially in equilibrium at lambda f, and I change that, I now decrease lambda f over time tau star to lambda I in exactly the manner which is time reversed, time reverse protocol of this one. That is, I take this protocol and I go backward in time. Okay, so I am unable to draw it, symmetrically. So how does it look like? Whatever it looks like, maybe it is like this, whatever. Okay, lambda I. Sorry, this is tau and this is tau star. You got the experiment? That here, what I am doing is that now I am starting with the system in equilibrium at lambda f and decrease, I am almost done. So, yeah, so I change lambda in the time reverse manner. So, what is the thing that you do? Well, we keep it as a mystery. Let's take it next time, because I see that I have run out by 10 minutes or something. Okay. You think about it and then we'll talk about it. sorry.
No problem, no problem.
Achha, I forgot to bring the sheet. So
Yeah, but